All right, so class, we are currently now in section 8.6. We have learned a lot about series in terms of determining where, when they converge, when they diverge. And in our last class, we talked about power series, which is section 8.5. So power series is where we look at series where we have the variable x in the series. And we find what are called intervals of convergence. And sometimes those intervals, incidentally, will, actually, they'll include the endpoints. They can include both endpoints of the interval or no endpoints. I mean, you've had some practice finding intervals of convergence. So now that we have a pretty good knowledge of series and power series from section 8.5, we talk about taking functions and expressing them as power series. And section 8.6, for a limited set of functions, we can take those functions and express them as power series. In section 8.7, we're going to learn a more general approach, but right now we're focused on 8.6. This is section 8.6 is the last new section to be covered on your fourth exam, by the way. So, all right, let me give you a moment to copy this example down. Okay, so what we have here is a rational function. Okay, we have a rational function, 1 divided by 1 plus x squared. We want to find its power series. Now, what you'll learn, well, I'm going to go to the whiteboard. What you'll learn here in section 8.6 is that you can take the function 1 divided by 1 minus x. Now, that's not the function for this example, but you can take 1 divided by 1 minus x, and that can be shown to be equal to 1 plus x squared plus x cubed, and so forth. In other words, 1 over 1 minus x will equal this power series when x is between 1 and negative 1. Another way of saying that is the common ratio x is less than 1. See, this here is a geometric series, right? This is a geometric series with common ratio x. All right, now you might wonder, okay, Dr. Duty, can you show why 1 divided by 1 minus x equals this series? How can that be? How can that be? Well, I'll show you here. I'll show you. So, are there any Well, let me show you. So, but I'm going to have to clear this. So I would put, take a moment, put this in your notes, okay? Put this in your notes. And we're going to show why this here is true. Okay, let me know when you're good, and then I'll clear the screen. And well, actually, no, I don't need to clear the screen. I can actually show this on. I have this on written out on my notes. So everybody's good. All right, let me go back to the notes here. Yeah, what we're going to do is, and I don't need the word. Come on. I don't need analogously there. So let's divide 1 by 1 minus x. So we're trying to show why that result's true. So I'm taking 1 and dividing it by 1 minus x. So how many remember dividing like rational, like doing this in maybe pre-calculus? If I have 1 divided by 1 minus x, yeah, 1 goes, Clay remembers that, 1 goes here, and 1 minus x goes outside. And 1 minus x, if we take 1 times 1 minus x, we get 1 minus x. And we're going to subtract the 1 minus x. And when we subtract the 1 minus x from the 1, the 1's cancel out, and you're left with negative x, so you get an x here. Well, 1 minus x goes into x times. X times 1 minus x is x minus x squared. You subtract that, and then the x's cancel out, and you're left with x squared. 1 minus x goes into x squared times. So you see, you just keep dividing, and you end up getting that series. You end up getting the series 1 plus x squared plus x cubed, and so forth. So that's how we know that 1 over 1 minus x equals that power series. And that power series, again, we recognize it as a geometric series with a common ratio x. Well, the power series representation of the function 1 over 1 minus x is only true for our interval of convergence. And the interval of convergence is the absolute value of x is less than 1. Or we could say x is less than 1 and greater than negative 1. Okay, so even though you can compute the function 1 over 1 minus x, I can compute that function for all values of x except x equals 1. I can't represent the 1 over 1 minus x, that rational function, as this power series unless my x variable is for values between 1 and negative 1. Okay, let me give you a moment to copy that. Let me know if you have any questions. Okay, may I go to the next page? All right, Clay is good. Franklin, how are you doing?
It's okay, Professor.
You're good?
Yes.
Okay, all right. All right, everybody's good. All right, so let's sort of summarize now what we have. So I have a formula that says 1 over 1 minus x is equal to the power series where n goes from 0 to infinity of x to the nth power when x is between -1 and 1. And what we're going to do is we're going to basically exploit this power series, this formula, to help us find the power series representations for different functions. So, like for instance, if let's say I had, you know, the function like 1 divided by 1 minus 2x. Okay, well, I can find a power series for that function, because based off of the power series formula that I know that if instead of x I were to like put in an apple, 1 over 1 minus apple would equal the series n equals 0 to infinity of apple to the nth power, so long as the absolute value of apple is less than 1. So instead of an x, I'm putting it for x and apple. And so like a function like 1 over 1 minus 2x, I would put 2x in for, and that would be like my apple. Okay, so we're going to need to utilize the apple formula to help us with the problem that we're working on. But I want to make sure that you're comfortable. So, you know, there are two formulas here, formula 1, and then the more useful formula, formula 2, which is based off of formula 1, the result. Well, so let's make, Clay, are you okay with the second formula? You're good with that, okay. So I'll tell you what, don't worry about what I wrote here. Don't worry, if you're good, if everybody's good with these two formulas, 1 and 2, then we can proceed on to solve this problem. Are there any questions? Okay. So let's remember where we are. Here's the problem at hand. This is the problem that we want to find a power series for. Okay. So I'm going to rewrite that function so that I can use the result that we just learned. So let me go here. All right. What I'm doing, and I'll let you copy this in a moment, is I'm going to, I mean, remember what I have here. I know that 1 over 1 minus an apple is equal to the series n equals 0 to infinity of the apple to the nth power. That's so long as the absolute value of the apple. So, you know, it's a geometric series with a common ratio equal to the apple. This function, 1 over 1 minus apple, equals this power series here, so long as the absolute value of the apple is less than 1. So what I do is for my function 1 over 1 plus x squared, well, I know to use a formula I need a minus. So I write positive x squared as minus negative x squared. I can do that. 1 plus x squared is 1 minus the quantity negative x squared, and negative x squared becomes my apple. Okay, and so therefore, using this formula here, I end up then with this power series, because the apple is negative x squared. Okay, let me give you, now remember, again, anytime you write a function as a power series, you have to worry about the interval of convergence. The absolute value of the absolute value of the apple is less than 1, so that means the absolute value of negative x squared is less than 1. But the absolute value of negative is a positive. Okay, so we get positive x squared is less than 1. X squared is positive, right? I mean, I guess here I could put in an extra step. Hold that question, Clea. Hold that question. The absolute value of negative x squared is less than 1 means the absolute value of x squared is less than 1. The negative goes away. Well, x squared is positive for all x, so I can write then that for the interval of convergence that x squared is less than 1, but x squared would be less than 1 only when x is between negative 1 and 1. If you draw a graph of x squared, here's x squared. Okay, well, so long as your x is between 1 and negative 1, the y value, the x squared, right? This is f of x equals x squared. That function will be smaller than 1 so long as x is between negative 1 and 1. So this is your interval of convergence. Clea, you had a question? Maybe I answered it. You're good?
Yeah, I just asked if like we had like the -1 comes from minus x squared, right? That's how we got -1.
The -1. Let me see.
Because we had minus x squared, so because of the minus, we have -1 times x squared.
That's right. That's
Okay.
right. Oh, and I'll show you what I'm doing here. Okay, all right. So, are there any questions? All right, I'll get down. Any questions up to this step? All right. Well, now what we want to do, traditionally, we don't want to leave our power series written like this. It's not in what we call simplified form. So what I'm going to do is I'm going to take the negative x squared and write it as -1 times x squared, still being raised all to the nth power. But then I can rewrite the series as the series where we have -1 to the nth power times x squared to the nth power. But x squared to the nth power is just x to the 2nth power. Because remember, when you raise to a power, you multiply the exponents. And so this formula here is the very nice little formula for our power series. And if we write out some terms, the first 5 terms of the power series, there you are. 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. Right? Because I'll just, it doesn't hurt to put it in the little recording here. All right, so 1, that's just x to the 2 times 0 power. X squared is x to the power 2 times 1. X to the 4th is x to the power 2 times 2. You see n's changing from 0, 1, 2, x to the 6 is x to the power 2 times 3. So you see where these terms are coming from. Okay, let me give you a moment to, I want to make sure you're able to, you know, copy and think and all that. So let me know if you have any questions. Okay, so in summary then, we can say that this function 1 divided by 1 plus x squared will equal this power series so long as x is between -1 and 1. Okay, so like for instance, like for let's say, you know, for example, if you wanted to find f of a half using the power series, that would be 1 minus a half squared plus a half to the 4th minus a half to the 6th plus a half to the 8th right? And so forth. But f of 3 would not be equal to 1 minus 3 squared plus 3 to the 4th minus 3 to the 6th plus 3 to the 8th. Why not? Why not?
Because we have 2n, so it doesn't make sense to have 3 because it's an odd number.
I'm sorry, Clay, I can't hear you quite. I mean, f of a half, this is fine. Well, no, the 3 is, I mean, it isn't, and Clay, I appreciate all responses. It doesn't have to do with the fact that 3 is an odd number. Look here. See what I'm circling here? This, well, Mark, you're on the right track. This is the interval of convergence. And f of 3, we cannot use the power series to evaluate f of 3. Why? Based on the interval of convergence, we cannot do that. F of a half is okay. We can use the power series to compute f of a half. That's right. That's right, Mark. 3. So a half is between 1 and -1. But 3 is not in the interval -1, 1. 3, okay, so, you know, a half is between -1 and 1. Okay, we love that. But 3 is not inside that interval of convergence. And so that's why you can't use f of 3. You can't use the power series to compute f of 3. But f of a half, you can use the power series for f of a half, because we can use the power series at x equals a half to compute the function at x equals a half, because a half falls within the interval of convergence. Okay. So far, so good, class. Are there any questions on that? And if you actually even look at f of 3, you got like, it's like going like crazy, right? It's diverging, right? I mean, there's no, I mean, when you think about it, if you were just to compute, you know, f of 3 using the function, you'd have 1 divided by 1 plus 3 squared, which is a 10th, right? But there's no way that f of 3 here, if you look to the right, there's no way that's going to give you a 10th, right? That's just not even going to work. So, okay. Are there any questions so far before we're going to try to see if we can get through 5 good examples here. Maybe 3 before the break, but let's just make sure everybody's comfortable. All right, let's do another one then. Here's another function. F of x equals x cubed divided by x plus 2. We want to find the interval, well, we want to find the power series and the interval of convergence. And incidentally, once you know the interval of convergence, you can get the radius of convergence. You just take the length of the interval and divide it in half, divide it by 2, and to get the radius of convergence number. I want to mention too, these problems here, when you find the power series for these problems, you don't need to worry about testing at the endpoints, because the apple formula, you know, 1 over 1 minus an apple, that formula is that power series is a geometric power series. So a geometric power series, you automatically know that geometric power series would only converge when the absolute value of the common ratio is less than 1. You don't need to test the endpoints or anything like that for section 8.6 problems for your interval of convergence, because that apple formula is that power series is a geometric series. Okay. So what do you think the apple is here? Well, I want to be a little bit careful here. We notice the 1 over 1 minus an apple, that formula requires us to have a minus here, but also a 1 here. 2 conditions that are not satisfied by this denominator x plus 2. Now with the x cubed, we can just factor that out. But the denominator, I mean, you know, what we have here, right, is x cubed times 1 divided by x plus 2. So the 1 divided by x plus 2, the denominator here, does not look like 1 minus an apple. So we have to make it look like 1 minus an apple. We have to manipulate it a little bit. So let me go to the next page then, and I'll show you the solution. so what we do is we take 1 over x plus 2 here, and we write it as 1 over 2 plus x. I mean, that's fine. And then to get a 1 where I need it to be, I'm going to factor a 2 out. So 2 plus x can be expressed as 2 times 1 plus x over 2. And you see, by doing that, I get a 1 where I need it to be. So now this function, I'm writing it as x cubed over 2 times 1 divided by 1 plus x over 2. Now I need a minus. I need a minus, right? So I'm going to write 1 plus x over 2 in the denominator as 1 minus negative x over 2. And now I have this part here of the expression is in the form I want it to be. Because remember, 1 divided by the quantity 1 minus an apple is equal to its geometric series with common ratio of an apple. And now this is in the form I want it to be. And so I can change the, hold on here. I can change that part of the function into an appropriate power series, where the common ratio is negative x over 2. Common ratios can be negative also, right? But remember, we require that the absolute value of the common ratio be less than 1. So that means, of course, if I put a little step in here, the absolute value of x over 2 is less than 1. So then that means then that if we multiply by 2 on both sides, we get then that the absolute value of x is less than 2, or x is between negative 2 and 2. So your interval, that's your interval of convergence. And that means your radius of convergence would equal 2, because the length of that interval of convergence is 4. I mean, this is, how many are thinking this is pretty nice math here, pretty interesting? It's pretty good stuff. I understand, Yonatan, I understand. It's certainly interesting. So, Mark, we worry about the endpoints. We worry about convergence at the endpoints for problems in section 8.5, those power series problems that you had that are now due on Friday. that's where you worry about have to worry about endpoints, but not for the section 8.6 problems, because the intervals of convergence, all these problems, let me take off, I don't want my email on here, I don't want it. All these problems are based off of a geometric series, namely this geometric series here. Mark, is that okay? Okay, you're welcome. Claire says if we say bigger, for example, right, so okay, so like this interval here from -2 to 2 doesn't include the endpoints. So we could write this as the open interval from -2 to 2. So all the intervals of convergence in section 8.6 are, for practical purposes, they are open intervals. I have to be a little careful what I say, but yeah. Are there any other good questions before I move to the next page? Okay, may I move to the next page? Everybody's good? Okay, very good. Clay is good. All right. So we're not going to leave our answer like you see it here. You're going to see that it's very important to get the answer, that summation in simplified form. Okay. And then the x cubed over 2, we're actually going to bring that back into the series. So we're going to bring it in. So here we go. Let me give you a moment to copy these steps down, and let me know if you have any questions. So of course, what I've done is I've really written out the math step by step, so you can see what's going on. Okay. Are there any questions regarding the work? I mean, regarding this work here. I will mention here that, you have so like this x cubed over x cubed divided by 2. I bring that inside the summation. I can do that because does x cubed over 2, does this term depend on n or not depend on n? X cubed over 2. So the summation starts at n equals 0 and goes to infinity. But is the expression x cubed divided by 2 in front, is that dependent on n at all? No. So this does not, that's right, Daniel. This does not depend on n. Does not depend on the index n. So that means we can bring it inside the summation. You could also think of going the other direction, right? If you were to start here you could go to here, right? Without too much difficulty. You learn that you can take constants. Well, x cubed over 2 has a variable in it, but with regards to the summation, it's like a constant, right? You've learned you can bring constants out in front of summations, right? Well, then you could also bring constants inside summations. So you can just as easily go from, here to here. So, and then you have a x cubed here, and you have an x to the nth power here. So it makes sense, x cubed times x to the nth is just x to the 3 plus n power, which I write as x to the n plus 3. Okay, so we get an alternating series here. Are there any questions about that math that you're seeing? Because in WebAssign in the homework, there's going to be some multiple choice, and the multiple choice answers are going to be in simplified form. So you got to simplify your answer down to simplified form. Are there any questions? All right, well, and then I wrote out some terms of the series. I wrote out some terms of the series for you. Okay, so let's see. Clay says, how do we get the 2n? Oh, okay, let me show you that. All right, let me clear this here. So in the denominator, you have a 2, but that's like 2 to the first power. So if I take 2 to the first power and multiply it by 2 to the nth in the denominator, 2 to the first times 2 to the nth is 2 to the 1 plus n, which is 2 to the n plus 1. Okay, very good. And then, of course, here, the first term is a half times x cubed. That's because, all right, negative 1 to the 0th power times x to the 0 plus 3 power divided by 2 to the 0 plus 1 power. That's going to be 1/2 x cubed. Okay, maybe I'll just circle that. The next term, negative 1/4 x to the 4th, how do we get that? Well, that's negative 1 to the first power times x to the 1 plus 3 power all over 2 to the 1 plus 1 power, which is 2 squared, right? That'll get you 4. Okay, and you can keep going. I'm just showing you, giving you a little detail here. How many kind of like seeing the series written out? You have the formula, you get your summation formula. How many think it's kind of nice to write down the first 3 or 4 terms of the series? How many feel that gives you makes it a little makes you a little more comfortable? All right, Clea likes that, and Daniel likes that. Great, great. Avery likes that. Wonderful, wonderful. So the interval of convergence, remember though, is from -2 to 2. In other words, open interval, -2 to 2. That's your interval of convergence, and the radius for this power series, and the radius of convergence would be 2, because that interval has length 4. Okay, let's do one more here. Any questions before we move to the third example? Okay. we want to find a power series representation for this rational function. Now, what makes this interesting is that the denominator has a square on it. Okay, that doesn't resemble the Apple formula at all, right? Again, let me write down again our Apple formula. 1 divided by 1 minus the Apple is equal to the geometric series. It equals this geometric series. And that's when the common ratio, absolute value of the common ratio, is less than 1. Well, what makes this problem hard is you have this squared term here in the denominator. So you're not going to be able to use the Apple formula, I like to call it, my Apple formula. You're not going to be able to use it directly. You're going to have to do a little bit of manipulation actually on the function in order to utilize that Apple formula. So, but we'll get there. Actually, we can effectively we're not going to manipulate the function, but we're going to reach the function in a certain way. So let's go to the solution here. And use the zoom key if you need to. The function, remember, the function was equal our function was equal to x divided by 1 plus 4x quantity squared. Now, we know 1 plus 4x is going to be needed. So let me just go ahead and figure out the power series for the function 1 over 1 plus 4x. That's not the function that we're interested in, but we'll get to the function we're interested in. So the plus 4x I can write as minus a negative 4x, and then the summation, the power series for 1 divided by 1 plus 4x is just the summation n equals 0 to infinity of negative 4x to the nth power, where the absolute value of negative 4x has to be less than 1, okay, for interval of convergence. That just means that your interval of convergence will be between negative 4th and a 4th. The negative 4x to the nth power, I can write that, well, you know, I'll write that here. Negative 4x to the nth power is just negative 1 times 4 times x to the nth power. That's negative 1 to the nth times 4 to the nth times x to the nth. That's what I get here. Please let me know if you have any questions. All right, now again, how are we going to get to this function that we're interested in? We're going to take the derivative of 1 over 1 plus 4x. So why is that going to work? Why is that going to work? Well, the derivative of that rational function, it turns out, you know, of course you're using the chain rule here, right? You're using the chain rule. The derivative of that rational function, which I write as 1 plus 4x to the negative first power, it turns out that equals negative 4 divided by the quantity 1 plus 4x squared. And that is nice because our function involves in the denominator the quantity 1 plus 4x squared. So what we can do then is, since basically, let me just see here. Maybe I'll put in a little extra step here. Hold on. If you hear clapping occasionally, it's because there's a mosquito flying around here. And, you know, I don't like to, you know, I leave bugs alone if they leave me alone. You know what I mean? All right. So one moment. Hold on. So the derivative of 1 over 1 plus 4x equals negative 4 divided by the 1 plus 4x squared. Okay. But up here, I want to say this the right way. Sorry, let me put it over here. No. Let me do this again. Hold on. Okay. So this is true. But this means then, this implies that the derivative of power series for 1 divided by 1 plus 4x okay, because all we're doing is we're replacing the function 1 divided by 1 plus 4x, we're replacing it with its power series. That's all we're doing. And that's how we get this result. When I kill this bug, it comes close. Okay. Just can't take a chance, you know. All right. So now the derivative of a sum, if you have, let's see how we go from this step to this step here. When you have the derivative of a sum, derivative of f plus g, the derivative of a sum is the sum of the derivatives, right? So here we have the derivative of an infinite sum. Well, that would just equal infinite sum of the derivatives. See? But inside, we have the derivative with respect to x of -1 to the nth power times 4 to the nth power times x to the nth power. The -1 to the nth power to the 4 to the nth power, do they depend on x? Does -1 to the nth power and 4 to the nth power depend on x at all? Or are they independent of x? No, that's right, Susanna. So we can go ahead and like just, write those down. Okay. We can bring them out in front of the derivative. That's what I'm saying. We can factor those constants out of the derivative. And then the derivative of x to the nth power is n times x to the n minus 1. And that's how we get this result here. Absolutely beautiful. Some of the most beautiful mathematics there is, you're seeing here. Now, the index, when I go from this step to this step, notice the index changed to n equals 1. And that's because if you write out if you write out the terms of this series, the first term is -1 to the 0, like when n starts at 0, -1 to the 0th power times 4 to the 0th power times 0 times x to the 0 minus 1, right? Plus then the remainder, the rest of the series. So what I'm saying is that series, you can write the first term, that's when n equals 0, plus the remaining of the series starting at n equals 1. But what's the first term equal to? What's this first term here equal to? No matter what x is, what's the first term going to equal? Going to equal, well, hold that thought. Are we sure it equals 1, this first term here? -1 to the 0th power is 1, 4 to the 0th power is 1. But look at what we have in there. There's a 0. That's right, Yonatan. See that 0 there? So that equals 0, the first term. And so that's how then we can say that the series starting at index 0, we can start it at index 1, which is what we have here. See, it's important to be able to recognize these things because sometimes in WebAssign, they write down like a multiple choice answer. They write different formats. And so, you might have to modify your series to start it, instead of n equals 0, start it at n equals 1. But then this is curious. This is curious. We get yet another answer here for the series. Let's see what's going on with that. Let me see what's going on. So how do we go from this series to this series? All right, I can show you that. I can show you that in the whiteboard. I can show you that. let me go to the whiteboard here. Are there any questions so far? All right. I just want to go to the whiteboard here. So there's a lot in this problem, but it's all the stuff you're learning is important. Okay, so we have this series here. And what we want to do is change the index from n equals 1 to n equals 0. But if we do that, we have to adjust all the n's by bumping them up 1. Hold on, I left something out here. I think this is the color I'm using. Yeah, red. So you see everywhere I see an n up here, I replace the n with n plus 1. And so that's going to get me then this series. And the reason I have to do that is because, like, the first series here starts at n equals 1. So, like, you have negative 1 to the first power, right? That's the first, like, you know, I want to say this the right way. I'm not saying it the right way. So, like, just like if we look at the first term of the series, of this series, is negative 1 to the first power. When you start at n equals 1, negative 1 to the first power times 4 to the first times 1 times x to the 1 minus 1 power. You need, for this series here, the first term to match that. Well, you're starting at n equals 0, so you'd have, you know, negative 1 then to the 1 plus 0 power. Well, that's a match. That's negative 1 to the first power. And then you have 4 to the 0 plus 1 power. That's 4 to the first. That's a match. N plus 1 would be 0 plus 1. Again, this is for the first term. That's a match. That's a 1. And then you have x to the 0 plus 1 minus 1. That's x to the 0. It's a match. So you see, when you lower the index by the index started at n equals 1. If you lower the index 1 to n equals 0, you have to raise the powers by 1. Okay, and you know, it's just important that you see that. So you have now that. Let me just see here. Yeah. So we're good. Are there any questions on that? Okay, this is all being recorded, but let's go back to the problem then. You'll see all this on your homework. You'll see all of this on your homework. Okay, so let me just clear this. Okay. So we've established that, I'll change the font again. Okay, we've established that -4 divided by 1 plus 4x quantity squared over the appropriate interval of convergence, that function can be expressed as this power series. Okay, let me just make sure. Give me a little more space here. Sorry. I like things to be very, very, very clear. So now we're going to utilize this to get our answer, and I'll show you how. The function, again, our function is x divided by the denominator 1 plus 4x squared. Okay. I can write that judiciously as -4 divided by 1 plus 4x squared times -x over 4. The -4 over the 1 plus 4x squared, well, we already found the power series for that. And now what we can do is we can bring in that -x over 4 in front. We can bring it inside the series, as I do here. All of this is important math. Okay. And then I want to just simplify things a little bit here. Okay, so I have a 4 to the first power here. Okay, I have a 4 to the first power here. And I have a 4 to the n plus 1 power here. We subtract the exponents. That's going to give us 4 to the nth power. Okay. I have a -x here, which I can write as -1 times x. Well, or -1 to the first power times x. -1 times -1 to the n plus 1 is -1 to the n plus 2. See? And so, you know, we get the series, we get the power series for this function. So we can say then we can say, in summary here, that our function, which was x divided by 1 plus 4x squared, that's going to equal this power series. So in this problem, we had to take a derivative. And I'm trying to keep, you know, you'll see this in your homework, a problem like this. And this example would be very helpful for you, right? Even if there's a help video, this recording should be very, very helpful. How many have gone back and looked at the recorded lessons from time to time? How many do that? Okay, Masume does. Excellent. Good, good. Keep in mind also that this is good over this interval of convergence, right? So I'll put a little comma there. And this is the interval of convergence. Absolutely beautiful, this math. Absolutely beautiful. The idea that you can take a rational function. The rational functions are usually difficult to deal with. How many remember those maybe in pre-calculus, that those functions tend to be difficult to, a little bit difficult to analyze and to work with. You had rational functions in pre-calculus, right? Right, does anybody recall that? Okay, thank you, Victoria. I taught pre-calculus before, so I know it's there. Hope Yemi remembers too. Okay, but now you're able to take these rational functions using your knowledge from section 8.6 and express them as power series, which are like polynomials, right? And polynomials are easy to work with. All right, are there any questions on this? Okay, let me stop the recording then. Excellent.